Okay, good afternoon, hello everyone. And the topic of my presentation is pattern-aware neurons. And this paper is published on ICCV workshop. So let's get started. So since the new members have joined, so let's quickly review the content of this paper. Minor pad, CNN can develop blind spots. Because some concept can be used in this paper, I'm going to present. So here's the thing. The researcher found that CNN-based model detector is capable of detecting a small but visible traffic light with a high score in one frame, for example, frame T. However, when a vehicle moves a little forward, the model suddenly fails to locate the traffic light. But as we know, CNN are often assumed to have translation invariance, and this issue aroused their curiosity. So if you place the traffic light in real yellow regions, the model can detect it and revealing a blind spot in the model. So as you can see, if you put this image slightly upward or downward, the detection score will sharply increase from 7% to 44% or 82%. Finally, they found that the existence of an asymmetry kernel in the CNN can cause light artifact, and resulting in the model being unable to detect the traffic light in certain regions. So if you forgot the content I present last time, here's a recorded video for you. And if you still don't understand what I'm saying, all you need to know is the conclusion. So in the minor pad, in this paper, the asymmetry kernel can cause light artifact and leading to a limitation to detect small objects in certain regions. So let's go back to our main topic. Today's topic is pattern-aware neurons. And in this paper, PAN is shown to introduce spatial bias to the model. And the concept of PAN is similar to that in a symmetry kernel in this paper. And the spatial bias is equivalent to light artifact. And this work makes several contributions. First, they propose a method to identify PANs through their activations. Second, they discuss and illustrate different types of PAN, their kernels, and their behavior. And third, they analyze their impact on the model. So here's the outline of today's presentation. And we are going to answer the following questions. What is a PAN? And how to find PAN? What do feature maps of PANs look like? And how many PANs are there in the neural network? What impact can PAN brings? And finally, I will present the conclusion, future works, and comments. So before we start, let's first take a look at the prerequisite knowledge regarding edge detector. So the definition of edge are the area within the greatest grayscale variation within small regions. So we mostly use derivatives or differentiation to detect edges. So common derivative includes first derivatives such as gradient and second derivatives such as Laplace operator. And here are some commonly used edge detection filters. So here I'll show you an example that we can use an edge detection filters to identify where the edge are. If you use these kind of edge detectors, perform convolution with the input here. The output with large value indicate the presence of edge. So when you apply this edge detector in these red regions, the output has a large value, 30, indicate that an edge exists here. So we often define a threshold value. If this value is greater than some threshold value, then we will identify that there is an edge there. Okay, so let's go to introduce what is a PAN. So what is a pattern-aware neuron? the definition of padding-aware neurons are convolution filters that learn to recognize the padding added to the input by some layer. And PAN can pass information on the border location through the network and introducing a spatial bias into model. For example, here are two examples for padding-aware neuron filters. And you can find that activation on left border location A here, if we put the kernel here, will give a larger output than in the center, location B. Because you can see that the negative part of the kernel is mixed by the edge formed by zero padding, here, zero padding. And this negative part are masked by 0. So a larger value is created when it is placed at border A. And PAN can react to one or more border of the input. This can include, for example, we put in the top or bottom of left, of right, but also any combination of these. So this example shows the type of left PAN. And here I show you a table that highlights the difference between non-PAN edge detectors and PANs. So non-PAN and PAN are types of edge detectors. Their neurons look for value contrast. And the non-PAN edge detector is maximized only when the value contrast is centered on the kernel. In contrast, nascent PAN maximize its output when the edge is located at the border of the filter in order to discriminate the padding edge from other edge in the input. The padding edge is formed by 0 padding, and the other edge is the edge which is in the image center, not at the border. So this kind of PAN can discriminate two types of edge. And here's another type of PAN is called downstream PANs. It reacts to the presence of padding as conveyed by PAN in previous layer, and they don't directly perceive padding values. And here are the examples of different kinds of PAN. And if you look at the PAN's example kernel, you can find that they have a characteristic of an asymmetry kernel. And notice that in this work, they only focus on nascent PANs. And in the rest of my presentation, PAN represents nascent PANs, and we won't discuss the downstream PANs.
What is nascent PAN?
它放在边缘的时候，它会有最大的输出，因为边缘通常如果用 real padding 的话，它会侦测到 real padding 的那个边界。那如果放在中间的话，就不会有这么大的输出。
这样叫 nascent。
对，就是它定义的。就它跟一般的 edge detector 的最大的差异就是它能够 detect 出在边缘的那个边界。downstream 是它不会直接 detect 出来，但它会根据前几层的 layer 给它的资讯把它拼出来。它没有直接碰触到 zero padding 的那个边，但它可以识别说前面给它的资讯说有那个边的出现。Okay, so the second question is to ask how to find a PAN. So let's separate the edge. Here are the steps for finding PANs. First, we need to separate the edge detector from the normal neuron first. So we need to find this line, how to discriminate these two kinds of neuron. And second, we need to separate the edge detector into PAN and non-PAN. And also we need to find this line. So, however, you might find it very difficult to identify a symmetry kernel directly because the complexities of characterizing PANs through their high dimensional kernels. So they decided to just use their activation instead. So it's too difficult to identify if a 3D kernel is a symmetry kernel. So they look at the feature map. And first, we need to find the edge detector. So the method is to record the activation for a given neuron, produce 5 regions, left, right, top, bottom, and center, and using a probability density functions while processing a batch of data. Notice that left, right, top, and bottom have direct access to the edge generated by geopadding. And PDF corresponding to the feature maps of 5 different regions are generated. So you will for each neuron, you will output 5 probability density functions, and only these 4 kinds of PDF will see the padding edge, but center will not see the 0 padding edge. So for each neuron, they utilize the feature map and plot it as a PDF to observe the distribution between left, right, top, bottom, and center to determine whether the neuron is an edge detector. So they conduct a KS test to evaluate the goodness of fit between 2 probability distribution. And the meaning of KS test is that if the KS test value is larger, the greater the divergence between 2 distributions being compared. So here's a little quiz. So there is one normal neuron and the one that look for value contrast, which might be an edge detector. So by definition, which neuron do you think is looking for value contrast? If you think the answer is the left one, please raise your hand. Okay. If you think the answer is right one, please raise your hand. Okay. Good. So the answer is the left one. And I will explain why this probability density function is the edge detector. So you can see that this distribution is more for, if you see top, bottom, left, and right, and the distribution is more different from the center. So which means that this neuron is triggered by the edge caused by the padding border, which is a 0 padding border. And for a regular neuron, there is no significant difference whether the neuron is placed at the border or at the center. So we can use this condition to identify if a neuron is an edge detector. So now we have already found how to find this line. And now we need to separate the normal neuron from edge detectors using, or we can separate normal neuron from edge detector using this formula. And now we need to find this line. How to identify if a neuron is pan or non-pan. So now we want to separate this. And here's a question. So can a KS test between a center and a border PDF distinguish pans from other edge detectors? So the answer is no, because a complete A center PDF is dominated by non-edge activations and cannot represent the distribution of non-edge edge detectors. So this question becomes to find a distribution that can represent non-pan. So how can we find this distribution? So the key idea is to exclude the non-pan using a KS test. But how to get non-pan edge detections distribution? Maybe we can obtain the edge detector distribution from a center distribution. But as we said before, the non-edge activation in a center dominates its PDF. So they propose a hypothesis that the center regions of an input will include as many edges as a pad border. So remember, the definition of an edge detector is neurons that look for value contrast. So they truncate a center by keeping only the k highest and the k lowest value of a center, which k is a number of values in a paired border. So the conclusion is that they truncate a center to a plus and a minus center, and these two distributions can represent the distribution of the non-pan edge detector. So to identify pan using a KS test with truncate a center, pan should have either stronger or weaker activation to the edge detector. So A plus center and A minus center represent the distribution of the non-pan edge detector. A pan's distribution must be either greater or lesser than this, or it may simply corresponding to a normal edge detector. So we can use these two conditions to identify if this edge detector is a pan or non-pan. 意思就是说，他们用 A center 的分布去取前面最大的值的分布跟最小值的分布，当做是一般的 edge detector 的分布，然后再看说这些 kernel 放在边缘的时候会不会有比这些一般的 edge detector 更强烈的分布，更大或更少。那如果有更大或更少的话，才能当做是 pan。因为如果没有更大或更少，那它就等于是只等于是一般的 edge detector， 因为它不管放在边缘或放在中间都是一样的，就没有比它更强的分布这样。
就是它在 edge detector 的分布里面，它再去看说那个 pan 有没有再有更显著的差异。
对，没错。So let's review how to find pan. First, we exclude the normal neuron using this condition. And second, we separate the pan from other edge detectors. And they set a threshold for 0.5 in the rest of the paper. So what do the feature maps of pans look like? So again, here's a quiz. One quick question. Which neuron is a pan based on two PDFs? And is the left one or the right one? If you think it's a left one, please raise your hand. Right one? Okay. So, good. So the answer is the left one. Because you can see the KS value here, it almost satisfies the condition listed in here. And the distribution is far away from the center distribution. So let's take a look at this kind of pen. This pen has a preference for a bottom and a top padding, which consistent with KS plus, lesser than KS plus top, bottom, and center. And this neuron, beyond being padding aware, is also corner aware. Notice that the left and right have a bimodal distribution, peaking at -10 and -4. This is caused by particularly strong activation on corner positions, which you can see that a high value is in the top and the bottom distribution. You can see the corner of these feature maps has a higher value than other value in the feature maps. And if we change the input of this neuron from zero padding to reflect padding, the neuron no longer detects padding. You can see the top, bottom, left, right distribution become aligned with the rest of the distribution if we change the zero padding to reflect padding. And the border of the feature map will not have the obvious value。就是它这边就是我们前面已经讲说要怎么找到对边缘zero padding 产生的边界会有很大反应的 neuron 了。那它现在就是说，那我们找到这个 neuron， 我们把它 input 的 zero padding 拿掉，我们改用 reflect padding。那 reflect padding 就是有点复制边界值，所以它边界的那个界限就不会那么明显。所以不会那么明显，就等于是虽然你这个 neuron 你这个 kernel 是 padding aware 的，但是因为你改成 reflect padding， 那个边界被抑制了，所以你出来的 feature map 就不会再有看到有特别的现象。
所以这个图的横轴是什么？
这个图的横轴是 activation 的值，
activation 的值，
对，
指的是
feature map 的值，
feature map，所以是 conclusion 完之后
对
的那个值。
对。
然后 y 轴是
y 轴是频率，就是出现多少次。我在想说，这下面的，就是每一条线的下面的面积应该是1，就是它频率的，就它假设13，就是它出现13的值的大概出现的频率是多少？
这个是你前面讲到那个 PDF。
对。
所以加起来是。
对，我在想说，它的下面的这个面积应该是要是1这样。
所以他去统计说，这个 convolution 完之后的 activation value， 它的出现的频率。好 ，OK， 所以当用 reflect 用那个 reflect padding 的时候，很多大的那个值就不会有。
它就不会有反应，因为那个边界就不见了。
所以哪一些线的分布被改变的最明显？
就是如果我们可以看这个紫色是原本只作用在中间区域的 activation 的 output 的话，这个紫色是 center。那可以发现说，如果你改成 reflect padding， 这些所有上下左右的这些分布都会跟中间没什么差别，就会全部变回来。就是
你刚刚说那个紫色的是？
紫色的是指说，紫色的是指说中间的这个的分布，就是它 kernel 都没有碰到zero padding 区域的这些 activation 的分布。
哦 ，OK， 所以刚刚不同颜色的线是这个图的不同区域。
对对对。
然后你最前面先讲的另一个 study 提到那个 artifact， 它那个 artifact 怎么连接到这个 padding 的位置？
就是因为我在想说，它这边你可以发现它有明显的就是不一样的地方，就是它 feature map 上会有一些差异。那其实我觉得，然后另外一篇的论文也有提到说，它也是有 asymmetry kernel 的，是因为有 asymmetry kernel 才会产生这种现象。所以我觉得这两个概念应该是一样的。
但这边指的特别是指那个 edge detection 的
edge detection kernel， 就是还是我最后再补充一个东西，我之后再说明。就是那我先只讲这个好了，就是它这边其实这张 feature map 其实就有点像上一篇论文的那种 negative 的情况，就是这是我刚刚提到说我本来没有要讲的另外一种 pen。那 这种 pen 在这篇论文也就只有这边有用到。那我介绍一下，就是 this kind of pen cannot detect by their approach, and it activates distinctively on the second highest row of the inputs, as if it was detecting the top padding from afar. And the truncated center plus distribution peak both at around 2 and 0. And A center can see the padding data, so the spatial bias is not directly included by pad itself. It receives the information about the image border location from previous layer and deactivate when the static padding is replaced with reflect padding. 那他这边讲的意思就是说，虽然 A center 它这个区域它没有直接碰触到 padding 的，没有直接被 zero padding 所产生的边界，没有直接看到，但是它可以根据前面给它的 input 去解码出这些东西，所以会造成说它 feature map 分布有这样的情况。
So the edge you mean in this work specifically talk about the edge between the figure and the zero padding.
对，就是它这边，就我刚刚前面有提到说就是 edge detector 又可以分为 pen 跟 non pen。那 pen 是它特别对于边界这种 zero padding 边界所产生的有特别影响的，它定义为 pen。那
一定是图的周围的。
对对对，他想要找的是这种东西。
所以他去找这个是为了什么？
他找这个是为了什么？是说它的影响吗？还是？
不是，就是说他去定义这个东西，然后他说要去 detect 这个东西，对，这个的目的是什么？
目的是什么？好像没有讲。
你说 why do we want to find pain？
好像没有讲。对。
你说他的背景，他的一些背景完全没有讲到说找这个要干嘛？
我觉得没有。但也许可以看，就是他做了什么实验，就是因为
他后面那个 impact 或是 conclusion 会不会就让我们知道这个事情的？
对他后面会做一些实验，说这个 pen 对模型有什么影响，这样可以。Okay, so here's another type of pen. It's L type. So the left is significantly larger than the right distribution. So you see that the green distribution is larger than the red one. So again, when zero padding is replaced by reflect padding, the neuron no longer detects padding, and the left and right distribution become aligned to the rest of the distribution. So how many pens are there in the neural network? So in this table, you can see that pen accounts for approximately 2% of all convolution filters, and in considered model, ResNet, MobileNet, and Google Net, with the CDA is set to 0.5. And later layers seems to include a remarkable amount of pens, likely influenced by the large number of neuron found there. And this could be influenced by reduced reliability of KS method when applied on inputs with a small width and height. But it could also indicate padding location, plays an important role on the final prediction. theta 就是它定义的threshold。那刚刚有说要找 pen 有2个条件，就是 ks test 的那2个条件。那它就是那个值要大过 ks test 出来的值要大过0.5，那它才算这样。So applying the method to thousands of filters yields hundreds of edge detectors and dozens of pens per model. So here shows the stack distribution of ks distance for the first and last 4 convolution layers of ResNet 50. And notice each neuron contributes with 4 values to each plot. And top with kernel, top with center, bottom with center, left with center, and right with center. So the ks distribution shown in figure 4 indicate most neurons have low ks value regardless of their depth, within a mean ks between 0.1 and 0.3 on all cases. And in other words, most convolutional neurons have no discriminate power between activation in the pad border and the center. Overall, the result indicate that potential edge detectors and pens neurons are a minority found in most layers, regardless of depth. So another question is to ask, what impact can pen bring? So here is the original model. So yellow represents the pen, and black represents zero padding, and blue represents the reflect padding. So in the ResNet case, they found about 2% is a pen neuron. And they create 3 more types of model without fine-tuning. First, they create a model called reflect model. They use reflect padding during the whole inference. So they replace all padding from zero padding to reflect padding. And the second one is pen reflect model. So the pens has been changed to use from zero padding to reflect padding. Third is a RAND reflect model. So they randomly replace non-pen padding with reflect padding in an amount equals to the number of pens. It's 2% in this case. So their first experiment is to verify whether pen introduce relative location bias to the model. So the method is to compare the softmax output of origin with loss of pen reflected. And because the reflect padding is used to ease the effect of pen. To be precise, they compute the order of prediction probability for each class and sum them. And there are 3 possible outcomes. First, if the odds is greater than 1, it indicates a higher confidence in the prediction of class C in the absence of pens. And this could be interpreted as padding being used as evidence against that class. And if the odds is lesser than 1, the value implies the padding is being used as evidence toward the class. And if there is no change in odds, it can be inferred that the class C doesn't rely on spatial bias. So they conduct the experiment on ILS VRC dataset. And the dataset is for image classification, and it has 1,000 classes. And the table lists all classes whose odds change by more than 7%. And remarkably, class 4, which padding is used as evidence against it, seems to be mostly fine-grained types, mainly animal species, and dogs, which hints at the relevance of padding or overfitting. Conversely, there are no animals among the cats that use padding as positive evidence. And another experiment is to verify if findings are related with the relevance of padding or with the noise or added by data distribution. So they consider the result while using the random reflex. And in this table, the x-axis represents each case, and the y-axis is the log of previous mentioned odds. So they simply do a log on this formula. And you can see that the effect of the pens has a greater impact than rand, indicate that the pen is the key to influencing the class prior. And then find that pen strongly alter the prior of most cases, which an equally sized random subset of neurons does not. And in conclusion, pen reflex seems to affect most cases to a large degree, and either positively or negatively. And the random reflex set effect on class is very limited. Only a few cases are affected. And they repeat this experiment with model reflect, and the reflect has changed the input distribution of 100% of convolution layers, whereas the previous two experiments, the random reflect model and the pen reflect model, have only changed 2% of neurons. As a result, the reflect model odds suffer more extreme change than either one of the above. So no tendency around which cases receive positive and which negative logs was found. In this particular experiment, they believe that the larger odds variance in reflect has due to with the noise added to distribution, rather than due to some intrinsic quality of how padding is used. So because of the class level analyze aggregate pen's effect on single prediction into class mean, so they also measure by sample. So to examine individual impacts, they identify samples with the largest output change, measured as Manhattan distance between the largest of the original and pen reflect models. So there are 5,000 samples in pen reflect with a distance greater than 4 from the original model, but there are only 13 in the random reflect. And the number of disagreement between models is remarkably low. The limited impacts pens have on samples which are not part of the model training set could also be the result of padding information being used for overfitting particularly hard training samples. And pen reflect affect more strength to order of magnitude for more samples than random reflex. Of those 13 samples, 12 of them are incorrectly predicted as tangent, which indicates the presence of this random chosen 2% of neurons for this class.
Justin, why did they use Manhattan distance?
他想就是看说，我换了 pad 之后的对每个 sample 的影响是多少？那他为什么选这个评估的标准？他没讲，他只是想看这件事情。So Finally, the conclusion, future works, and comment. So this paper reviews the extent of inductive spatial bias, identifying a set of neurons specified in detecting and exploiting it, which they refer to as PANS. An experiment indicates padding information is used to change the prior of most classes, and PANS seems to be used as evidence against fine-grained cases, and seldom as evidence for them. Finally, let's examine a safety issue with PAN. Because of their specific patterns, PANs are easy to trick and activate. Adding a single row or column of zeros anywhere in the input can cause PANs to trigger unexpectedly and behave unpredictably. And future works. For the ILS VRC test, they derived two different hypotheses for explaining this. First is that either samples from fine-grained class are generally better framed, which keeps the padding away from the pattern most relevant for the class, resulting in a spatial bias that can be leveraged. And second is the padding is used as a reference to identify arbitrary patterns in particularly hard samples, helping open fit on samples from long tails. And it remains to be seen how presence of PANs affect in downstream tasks different to classification, such as training or fine-tuning for object detection, or whether fine-tuning in a new test removes or adds more PANs.